Welcome back. Today we shall continue again with cyclohexane, but with the point that I want to emphasize in this session is the representation that you see in a textbook and the models that we have shown, they must be correlated properly and you should not have any confusion regarding that. If you remember, with the help of models we have seen about the cyclohexane structure, chair form, if you remember. Now, as I told you, we'll try to represent the same thing on paper as faithfully as possible. For example, I want to show you now this. If you carefully watch out this, can you see two parallel lines here? Two parallel lines here. Hope that is clear for you. Two parallel lines. Draw them first. Then what I will do is I will try to combine this corner with the other corner, diagonally opposite to that. I will draw in the mind a straight line combining these two opposite diagonal points. A slight projection I have shown in fact there. I will not implement that idea of connecting both the points. What I will do is I will draw only 1/3 of this line from either end, only 1/3 of the line from either end, unfinished. And that unfinished line I will try to combine with the opposite side. For example, you look at this diagram. I have started from this. This is a 1/3 line. I should have continued like this, but I am not doing that. I will try to combine with this one. Such that I am getting a skeletal framework for 6 carbon system, which will help me to show a very good staggered conformation for cyclohexane type of molecules. Now if you focus on each of the carbon atoms, for example, imagine I am focusing on this carbon, this particular carbon. We can start with any carbon. I am showing this carbon. Now if you watch out here, the line that is combining here, this line is moving up. This line is moving up here. Remember, each carbon can form two type of bonds with CH. One is axial and other is equatorial. First we'll focus on the equatorial bonds here. So if this line is moving up, the other equatorial line I am drawing here, slide down. This is moving up, this has to move down. Hope that point is clear. If this line is moving up, this should move down. Similarly, watch out, this line is moving down, so this should move up. Similarly, watch out this line here, this is moving up, so this should move down. Similarly, this is moving down, this should move up. Focus on these 4. The slant line is what I have drawn, and I have drawn only 4 slant lines to focus with. That means I am left out with 2 more that I will finalize in due course of time, within this session only, of course. Now, if you remember, if I have drawn a slant line here, that means equatorial bond has been taken care of. Then what is left out is an axial bond. Remember, axial bond is always represented by straight line. Because this slant line is coming down, that must be moving up. Similarly, watch out this here. This slant line is moving up. Therefore, that axial bond must move up. Go to this corner. This is the equatorial bond. Therefore, the axial bond must be up and down, up and remember that point. This one, equatorial bond is moving up, so axial bond is down. Therefore, we are able to take care of 4 carbons very clearly with the way CH bonds are oriented. Now, where we have connected both the points here, try to follow. This is another carbon atom here and another carbon atom here, because cyclohexane means we require 6 carbons. This carbon, what I have done is, already 2 bonds are shown with carbons. I require to show 2 more bonds here. So what I have done here, because this line has moved up here, I want to draw the line down here. Similarly, focus on this is moving down. Therefore, this line must move up here. Once you draw axial, equatorial is not difficult. Watch out. This is axial and this slant line is equatorial. I have drawn towards the right side. In case if you are drawing towards the left side, no harm. Either way it is correct. You can take care of either of them. Similarly, for the other side also, equatorial and axial bonds is what I have drawn. Therefore, if you watch out, I have taken care Each carbon has axial and equatorial bonds. Once this is clearly drawn, we are very close to chair form. Suppose if I am viewing the molecule from this side, this is the viewpoint. Opposite this axial bond, I don't see any axial bond here on this carbon. This is down. Therefore, I have faithfully stuck to staggered conformation. Hope that point is clear in the mind of all the viewers. There is another alternative also. For example, if you focus on this area of the molecule, this particular area, and this particular area, I am showing in hand also, this area, and this area. Are they looking identical staggered forms and of ethane that too? For example, there are two carbon atoms here and there are two carbon atoms here, and try to follow, this is moving up, therefore this is moving down, therefore this is staggered form only. Another way of appreciating the chair conformation is, imagine these are two staggered identical ethane forms. And if I stretch out this line here, they will combine here, and there you place one more carbon and take care of the staggered conformation. Even this way, we'll get a beautiful staggered form. And this, we remember, we've called this as a chair form. Now, what is the meaning of chair form here? Very comfortable position for all the atoms. That's all. Figuratively, you should not imagine a chair here. Nothing like that. It means all hydrogens are staggered. Therefore, there is no strain in that molecule, and the bond angle has gone for every carbon atom to be 109. Therefore, it is extremely stable molecule. Of course, it can move up and down. We can get different types of other conformants also, like boat form, half twist form, etc. But right now I am focusing only one of them. Others, please try. If you are not getting, let me see what we can do. Hope this diagram is clear for you. Initially I have drawn parallel lines and I did not combine them. This one, this corner, this corner. Only 1/3 and 1/3 line I have drawn, and that unfinished line I have combined with not with the expected line but from the opposite side. Therefore I got a framework. Under that framework I have ensured I am drawing equatorial and axial bonds in each one of them such that no two identical adjacent locations will have axials coming up. That will be eclipsed. So if you take care of that, I think you can draw the chair form quite comfortably. The other way, and one more point I wish to add at this stage is, suppose imagine, always that is the correlation I am trying to bring here, the diagram that you see in the textbook and the model. For example, here I have drawn methane molecule CH4, and this is the textbook representation. What you have below is the textbook representation, and this is the perspective formula for that. That means the carbon is in the reference plane. How do you interpret that three-dimensionally? The hydrogen coming top and bottom, this is the top position and bottom position, they are away from the weir. Please bear that in mind. And hydrogens or any groups that are represented right and left of the carbon, remember they are projecting towards you. Therefore I have indicated with a wedge-shaped line here. Even though I have used a single carbon system, the convention is same. Carbon atoms shall come in the plane, and the top group and the bottom group are away from the weir, and groups that are placed right and left are projecting towards you. This is the typical Fisher projection formula, and it must always conform to eclipse. Now I have shown here a big molecule. The molecule name is C6CHO, CHOH taken 4 times, and CH2H. That means what is my first carbon here? CHO, and the last is CH2H. These two are away from the weir, and I have shown 4 carbons here. These 4 carbons are in the plane of the reference, and H and OH are projecting towards you. Just check out whether I have faithfully carried that. You can make out CHO away from the weir, CH2H is also away from the weir, and the rest of the 4 carbons are in the reference plane with HOH projecting towards the weir. Hope you are getting 3-dimensional visualization of a ordinary textbook representation of a Fisher projection. That is necessary. Otherwise, the very purpose of my earlier sessions will be lost. Are you getting that point? So this is how we understand the textbook representation in reality, like this or like this. The third one I want to share with you is like this. Again, what is the emphasis here? A textbook structure and our visualization should not contradict with each other. Suppose if you watch out here, I have taken a molecule C, H, Cl, Br and I. This one. C, H, Cl, Br and I. That particular carbon, only one carbon is there in that. And with all 4 different groups, if you remember, that is a chiral carbon. And what is the point we have understood at this point? Such a molecule will have another molecule in nature with which it enjoys mirror image relationship. And the beauty is you cannot superimpose them. If you cannot superimpose them, that means they are independent of each other. Now this is what I have shown. What you see in the dotted line here, dotted line is the mirror plane. Are they looking like mirror images? Yes. Now point 1. Suppose if you are not sure about what you are doing, there will be mistake in that. This is not planar molecule. This is not a planar molecule. Now when we talk about superimposability, suppose if you take this figure and try to lift out from the page and keep it here, I think our bromide will come exactly over bromide. Iodine will come over iodine, and you get a misinterpretation of this textbook representation. That should not happen. Imagine the type of planar structures we have put here, they are not existing, is it not? So if they are not existing, where is the question of lifting them out? Don't do that. You allow this molecule, don't take out the molecule from the plane. Take this molecule, let it slide over this, such that what will happen, over bromine, I will get iodine. And over this iodine, I will get a bromine. That means they are not superimposable. Got my point here? Let there be no confusion. That's my point here, between the actual model and this thing here. Now I want to take a slightly bigger molecule. Can you see the next one? 2-bromobutane. 2-bromobutane. And I have written here CH3, CH over carbon I put a star, then Br in the bracket, CH2, CH3. Now this particular 2-bromobutane has a chiral center at the second carbon. Now what is the meaning of a chiral center here? In that case, if you correctly represent that molecule, there must be another molecule with which it enjoys mirror image relationship. I have opened out that area. Earlier in the condensed formula, they are shown together. That is, I have shown CH and Br together. Suppose if I show like this, in this format, watch out, what did I do here? I have put a cross, the convention, remember, I am not indicating carbon at that cross junction because that is a chiral carbon. I have H up above and Br down. Next molecule, the reverse of that, Br up and H down. Now this particular molecule, which is the chiral center, there are 2 independent molecules for this. 2 independent molecules. And these molecules are confirmed, they are experimentally confirmed to be present in the lab. We have one experiment called as polarimetry experiment, by which you can identify the presence of these molecules. Briefly, the polarimetry experiment is what? We take a special type of light which is called as a plane polarized light. Suppose if plane polarized, that wavelength will move in one direction only, like this. Now suppose imagine this is my sample molecule, and if this small radiation is coming and striking this, the direction of this light after coming in contact with the molecule which is having a chiral center will get deflected towards the right side or will get deflected towards the left side. I repeat, suppose if I am taking an optically inactive molecule, imagine this is an optically inactive molecule for me, inactive molecule. And if the plane inactive, that means no chiral center. If the plane polarized light falls on this, it just follows. There is no deflection, no change in the direction of the plane polarized light. On the contrary, if I take a sample which has this chiral center, it is sensitive to this optical phenomena, light phenomena. Therefore, these molecules which have a chiral center are also called as optical isomers, or they are known to show optical activity. Suppose if the light is getting deflected towards the right side, then that particular molecule is called as dextrorotatory molecule. If the plane polarized light gets deflected toward the left side after it crosses the molecule, then the left rotating molecules are called as levorotatory molecules. Dextro and levo, experimentally known. Of course, there is another way of naming these molecules which is called as RS notation. Right now I am not considering that, but once I intend to take optical activity in greater detail, probably I will go into many more details about that. For the time being, let us quickly resume what we have done here. We said we must overcome the model representation of the molecule and what we write on the paper. And let there be no contradiction in that. This is the cyclohexane molecule and this is the molecular model for that, and I must be faithful in representation, as far as faithful, such that we are very true to the actual configuration, conformers about CC bond, etc. All those details will be forthcoming. And secondly, if I have a molecule like this, a Fischer projection, how do we actually visualize that molecule? What is the positions of the topmost group and the last group there in a Fischer projection three-dimensionally? Of course, compared to Fischer, we have Sauer's formula and Newman, which are better, but normally you tend to encounter Fischer. Therefore, I thought you must be very clear in the actual visualization of the textbook structure. And the chiral center molecules you cannot superimpose. I told you, let them slide over each other, such that the confusion areas are minimized. And experimentally, one of the molecules is dextro-rotatory, other is levo-rotatory. By inspection, we cannot say which is dextro and which is levo. That must be concluded only after you carry out the experiment with the help of a polarimeter. At this point, we shall stop. We shall continue next time. Thank you.